Woohoo! We're off to the next assignment, and now we need to keep on a truckin' with TLC and HPTLC lecture discussions and how these things work and all of the details and the intricate little steps that go on in this entire let's put something on a plate and let it develop. I mean, it is often really delivered in a way that is very simplistic, and it should be very simplistic, and that's what you'll see when you first do your like very first plate. But there's so much more that is going on that's more than meets the eye if you were an 80s kid, and if you know what that means, high five. All right, so as far as the next assignment goes, we're going to now take a look at sample preparation, and we're going to talk about the best ways to prepare a sample and what I should be looking for and what I should be watching out for. What are some of the tricks of the trade in order to get that sample ready for plate development? That's what this is going to all be about. So with that said, I want to kind of tell you, well, if you have heard of this before, folks, it is the KISS method. And the KISS method means keep it simple, stupid. That's what this is. All right. So whenever we go through the sample processing that's taking place in a lab environment, and I need to get these samples ready to be applied to a plate, then we're going to remember, keep it simple, stupid. So that way this KISS method can be performed. What we're actually talking about is we are talking about very simple solvents, and we want solvents that are very cheap, that doesn't cost a lot of money, and we want a really low number of solvents as well. So I don't really want to go through the steps of, you know, having 5 or 6 different things that I've got to mix together to get the sample in its kind of final form. I want just one solvent or maybe 2 solvents that will get it into its final form, so that way we can apply it onto the plate. And when I choose these solvents, I want to be very cost effective. I want to make sure that these solvents are fairly cheap, that they're not going to be very expensive for a laboratory to order and to use, because, you know, there is a little bit of waste, and I just don't want to be wasteful with those really expensive types of solutions that can be out there that we can order, and that do a great job with TLC and HPLTC. Absolutely, they do a great job, but they're just not cost effective, and it's going to burn through money, and nobody likes to burn through money. You don't like to burn through money. When you get your paycheck, I hope you're not the one that's going to go out and be like, woohoo, let's go to the bars, we're going to spend all of our money that we've got. No, I hope you don't do that kind of thing. I hope that you're at least a little bit reserved. I hope that you're a little conservative with your money as you begin to make it and as you just start depositing into your bank account. And the same thing are with companies. Companies want to be very conservative with the funds that they are spending out, because all of that money can be recycled back into the company, hire more people, expand more business, give you maybe pay raises, who knows what the case might be, but they are really scrutinizing every single dollar that gets spent at these companies, and they should, because if it was your company, you would do the exact same thing. Next up, all of these samples should be homogeneous. All right, so homogeneous, well, homogeneous, and again, it's tomato. It is sometimes very Appalachian accent that comes out, and that I'm okay with that. Whatever, I don't care. But homogeneous is something that's going to look the same from top to bottom. So what that means is that if I get a sample in a test tube and I've got some liquid in there, then the entire thing is going to look the same from top to bottom inside of that test tube. There should not be any kind of floaty particles around. There should not be any lumps or any type of solids that settle to the bottom. So if I'm really doing the sample justice, then this is kind of how I want to process these samples, and I need to ensure that they are homogeneous before we go and apply them to the plates. All right. Next up, some extractions will probably have to happen. Now, these extractions might not be simple. The solvents that we are choosing, we want those to be simple. We want those to be cheap. But the extraction process could be very complicated. And I'm going to put could be in quotes because, you know, not necessarily is it very complicated. It might just take a lot of time. So that's okay. I can deal with that. If the company can deal with that, I can too. So I can process these samples. It's going to take me a little bit to get them into their final form. If they do that, then that's great. I hope that they look homogeneous by the time they get into their final form. I sound like a video game. Brutality. When they get to that point, then we can apply them again to the plate a little bit better. So we actually want to pick things that are not going to react with the sample that I am trying to process. You know, we got to be very careful with the solvents and the processes that we're using to take care of these samples as they're coming into the lab. And I don't want to do something that will react with the sample, because if it reacts with the sample, then no longer is it that sample anymore. It is now being reacted. It is changed into something new. And that's something that we just got to deal with in a regular laboratory setting every single day. So this idea should never go away on you. We should actively be thinking about it all the time. And HPTLC and TLC tech is no difference here. So we want to make sure that we're doing processes and we're picking solvents that will not change the actual structures or the identities of these components that we are trying to measure and that we're trying to analyze. Next up, they should, ding ding, they should be easily removable from the plate. And when they're easily removable from the plate, that's great news, because that means evaporation is taking place. That means that these things are very volatile. They can escape the plate without too much effort at all. And the reason is because when I develop these things onto a plate, wherever that solvent or mobile phase or developing solvent goes to, then this is going to lead me with some spots. And the longer that that liquid stays on the plate, then this can actually keep traveling up and up and up and up and up. And I just don't want that to happen. I want these solvents to be dried off quickly, so that way we can actually say, no, the development stopped at this moment in time. I took the plate out, I hit it with some heat, and that could be from a hairdryer. But I've hit it with some heat and I've evaporated off of these solvents. So that way I have stopped the migration of the spots. And if I can stop the migration of the spots sooner rather than later, I get typically better separation, it's better reproducibility, and my solvents are disappearing very quickly. So it really fine-tunes the TLC method and the HPTLC method as well. All right, here are some common solvents that we are going to see in a laboratory setting. And these solvents are things that you've seen many, many, many times. There's no surprises here, right? So water, ethanol, and methanol are going to be up here at the very top of the slide. And then we get another chunk of ethyl acetate, dichloromethane, and ethers. And then down here at the very bottom, I see some toluene and some cyclohexane. So water, of course, is H2O, and then ethanol is CH3CH2OH, and then methanol is CH3OH. So what we're playing around here with in the top category are things that are very polar. These are straight up polar solvents. They do a great job dissolving many things that we need to do in a laboratory setting. And it is going to be very, very common for me to see one, if not more than one, of these getting used in developing solvents, in the mobile phases that we're talking about, and also in the solvents of the samples that we're trying to process. So that being said, I don't really want very often drastic differences between the solvents that are being used in the sample processing and the mobile phases that are going to be used in the TLC development. I really want them to somewhat go hand in hand if that is possible. Next up is ethyl acetate, dichloromethane, and ethers. So ethers, of course, are going to be this ROR, and this ether functional group has two free sets of electrons here in the middle that's surrounded by some random alkyl groups. This is a nonpolar and polar type of mix. Those R groups cover up the free pairs of electrons quite a bit, and because of that, ethers can notoriously be known to be more nonpolar than they are polar, but they do carry attributes of both of these kind of different groups or families of molecules that we want to talk about. Methylene chloride, dichloromethane. So methane is CH4 is methane, but dichloro means that there's 2 chlorines on it at least. And then 2 others are going to be the hydrogens that were there with methane. So we rip 2 hydrogens off and we replace it with 2 chlorines, and there's DCM, or dichloromethane. That is what that stands for, also known as methylene chloride. Again, the free pairs of electrons are surrounding the chloride. So here we go, there they are, and those free pairs of electrons are creating polar areas of the molecule. And this is somewhat unequally distributed, right? It's not in the entire molecule all the way around. Depending on where the chlorines are going, they very much so are lopsided in the geometry that they take form of, which is going to be like a tetrahedral type of molecule. And there's always going to be a lopsidedness to this molecule for the most part, where these electrons are going to be located. And on the other side, or the other half of the molecule, we see just simple little hydrogens, no free pairs, no polarity that we can talk about there at all. So again, this is nonpolar because it's carbon-based, and it's also polar because there's free pairs of electrons that are at play in this chemical structure. Ethyl acetates, all right, so acetates, 8s are going to be esters, and we know that these esters will have these types of functional groups that look like this. These ester functional groups, they do carry free pairs of electrons, absolutely they do, and they are around those oxygens, but delocalization, like we've mentioned before, is at play. And delocalization means the electrons move throughout that area because those electrons see a house down the street that has more electrons in it, and they want to get out into the street, and they want to play, and they want to go to each other's homes for sleepovers, and that's perfectly okay. The molecule enjoys that, and you would enjoy that if you had hellion kids at your house, and you wanted to kick them out, and you wanted to go spend the night at somebody else's home for a change and give you some peace and quiet. So the molecule becomes very, very happy, just like you would if you had those mean little... But it is surrounded by R groups as well, and those R groups are, again, the organic pieces that cover up that delocalization, cover up those electron pairs that begin to move. But again, at the same time, we've got polarity and we've got non-polarity both at play, and we get this kind of middle realm here where these things are very well suited for many different types of components that we want to extract out of our samples, because that's what this is all about, folks, right? We're talking about bringing a sample in, extracting the things that are the most important. How do we do that? Next up is toluene and cyclohexane. Toluene and cyclohexane. So toluene is like a benzene ring, and then off of this is a methyl group, and then cyclohexane is almost kind of like that, but cyclohexane is just a 6-membered ring. That's all that it is. There's no double bonds on the middle. It's not a benzene ring. It is just 6 carbons in a ring, and that is it. So all carbons and all hydrogens. Both of these versions are pretty much nonpolar across the board. There's no free pairs of electrons that we can talk about. The electrons that are involved in the benzene ring, those are delocalized, which means it actually spread throughout the entire molecule, and their presence is not as noticeable because of that. So it stabilizes the molecule. There's not a lot of reactions that can happen with these types of situations, and that's okay. Sometimes we don't want those happen. We can get benzene rings to react, don't get me wrong, that's the basics of organic chemistry, but these, at its heart, at their nature, are non-polar. So again, very common solvents that we can use with samples that are given to us in a lab, and we want to process those samples, and we want to extract the things out of those samples that we want to pick up on a plate. And these are a very good assortment, a variety pack of very common things. They're not hard to get, and they are fairly cheap, absolutely. So it's not going to break the bank when these companies begin to use them. Some other types of pairings, if you want to call those, with these solvents. So sometimes one solvent's not good enough. You need actually a mix of different types of solvents. That's perfectly okay. No one says that we can't have that happen. So in the first category, what you're seeing here on the left-hand side are things that they call neat solvents. And a neat solvent is just pures. That's all that these are. It's just a fancy word to say pure. So I see acetone and acetonitrile and ethanol and methanol and water. I see ethyl acetate and dichloromethane. Tert butyl methyl ether, that is also there. Some people will abbreviate this as TBME or METB, because they just like to play around with the abbreviation, I guess, to make everybody confused. But all of these are very neat solvents. So nothing is going to be mixed. It is just that poured out straight out of the jug, not an issue at all. And those make great solvents that we can use and pull components out of these samples from. Next up are mixtures. Mixtures are going to be very important as well. So we can combo these: heptane and toluene, ethanol and water, methanol and water. Of course, this list goes on and on and on. They're just giving you some examples here. That's all that's going on. And these mixtures can also be used as great solvents. So this is an idea where one solvent is not going to be strong enough to do the job that we need done. So we're going to combo it, and we're going to bring in maybe two solvents, and we're going to mix them together. And maybe the power of those two solvents working together hand in hand can get the job done a little bit easier. It's just like the workplace environment, right? So if we want to extract these components, whatever they might be, from the samples that are given to us, mixtures are perfectly okay. They are very commonly as a go-to. Absolutely, they are. Second column, you're going to see acidic mixtures. And acidic mixtures, of course, are anything that have acids in play. The most common type of acid is going to be acetic acid, and this is glacial acetic acid. And glacial acetic acid means it is as concentrated as it can get. So you cannot go any further than this. I mean, this is like, I think, if I remember correctly, over 99% pure of acetic acid. Very little water in there, compared to something like hydrochloric acid, which is mainly 36 to 37%, or some of these other acids that I'll be using in a laboratory environment. Acetic is very strong. So that's what we call glacial. And this is kind of giving us a ratio. It says 9 to 1. Okay, so that means 90 milliliters of methanol and 10 milliliters of acetic acid. Or we can say 9 milliliters of methanol and 1 milliliter of acetic acid. Or we can say 900 milliliters of methanol and then 100 milliliters of acetic acid. It really is just to scale you up or to scale you down as needed for whatever sample solvent amount that you will need to extract those components for you. So that's why they like to give you those in terms of ratios. Water and acetic acid, again, very, very common. Methanol is a little bit of carbon, so there's a little bit of non-polarity there. Water is straight up polar, so I don't really see non-polarity there at all. So again, we're playing around with what works best for the components that I want to extract out of the samples as they're giving to me in a lab environment. Well, if we've got a basic column or an acidic column, we can also have a basic column. And what you're seeing here is the common go-to base is ammonia. So the reason that ammonia is chosen and the acetic acid is because, again, they are fairly common. Most labs have these in stock all the time, and then they are fairly cheap, so they're very friendly on the pocketbook. And then the ammonia, of course, is NH3, but the ammonia is really coming from NH4OH. This is the liquid that's in our bottle, and this is our ammonia source, and that ammonia that we're referring to is NH3 that's here. So we can weaken that down, absolutely. It says 25%, whatever the case might be. Well, ammonia that you buy in the store at Walmart or the Dollar General, that is a watered down ammonia solution that you're using to clean your house. And the same thing can happen here in a lab environment as well. We just order concentrated versions, and we weaken those concentrated versions down to a point that actually makes sense and that begins to be usable for us. Notice they do the same thing, methanol and water, so I can mix it with a little bit of polar or a little bit of polar / non-polar from the methanol piece that we're bringing to the table. Just as before, they love to give me ratios, so 8 and 2s. Well, that's 80 and 20, or that could be 8 and 2, or that can be 800 and 200, or that can be 8 liters and 2 liters. For all I care, it does not matter. So the amount of volume is perfectly okay. I'm not really worried about that. It's just giving me a ratio and how to mix things the proper way. Extraction techniques, I just told you, keep it simple, stupid. Okay, so these KISS methods are things that you've done in our laboratory up to this point if you've taken some of our other laboratory-based courses in the chemical technology program. The one that might be new to you is this maceration or maceration. Again, tomato, tomato. And this is just the idea of, hey, I'm going to make a mixed drink. It's Friday night. I'm ready to celebrate. I don't have to grade any papers. Woohoo! So what I'll do is that I'll grab a strawberry, and then when I grab a strawberry, I'm going to mush, and just basically make it into a paste, and then I'm going to add a little bit of ethanol to it. Woohoo! So that ethanol is going to be added to that sample. I'm going to mix it around, and then when I mix it around, I have macerated that strawberry. So I have mushed it up into a little slurry that I can then add other stuff to it and make it a wonderful mixed drink. And if you were out in public and you were at a restaurant, they would probably charge you $20 or $25 for this type of mixed drink. And that's all that it is. Mush it. That's it. Next up is reflux and soxylate. So reflux and soxylate, you know what those are, right? Refluxing is heating over a period of time. Soxylate is the multiple extractions. So we did that with peanuts. Like if you've taken our CTC 145 course, it is add some solvent, let it drain, add some solvent, let it drain, add some solvent, let it drain. And it just repeats that process over and over and over and over and over. Again, the idea is extraction here. So I'm going to be using solvents in all of these methods. They're going to be extracting components out of the sample in some form or fashion. And then that is what I'm going to get ready to go to my plate and get ready to develop them. Steam distillation's great. Steam distillation, we've done that before. This is essential oils, absolutely. And those essential oils were things like clove oil if you've taken our CTC 145 course. That steam distillation is let's crush up some cloves, let's put them into a steam distiller, and then let the steam do the work. So the steam goes much higher, and the steam will release that essential oil, and then it will carry over with this vapor, and we will collect it, and we will clean it up. So a great way to extract essential oils from complicated samples like plant material, absolutely. Shaking, very simple. I don't think I have to explain that one. Ultrasonic bass, it is just sweet vibrations. Woohoo! Sweet sensations. It's just vibrations. That's all that this is. So it's going to send vibrations through your sample and just helps break it up and jiggle it. When I think of ultrasonic bass, I actually think of like the old-timey, let's kind of stand on this table and put the kind of waistband around me and hook it up to a machine, and it just jiggles me back and forth. Jiggle, 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 jiggle. Because they thought that that would lose weight back in the day, and I guess, you know, people were like, woo, this is the greatest thing. It's like the infrared light face mask that I want to use. Woohoo! But it is ultrasonic, and that's kind of what's happening. So it's just jiggle, 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 jiggle the sample and breaks it loose, and it allows those solvents to extract those components into the solvent a little bit better and a little bit more efficiently. Next up are water baths. I don't think that I have to explain these as well. You crank the water on, get it hot, and then place your sample in the inside of a water bath, so that way it can kind of take over. It gives you a nice little jacuzzi tub, and that jacuzzi tub will start to leach out those components that you want to analyze onto a plate. Liquid extractions, this is sounding fancy, but it's not. These are just separatory funnel extractions. That's all that these are. So separatory funnel extractions, you add your juice into the separatory funnel, and then you add a second type of solvent inside, and that solvent is specifically tailored to grab the things that you are the most interested in, and it leaves behind all the other crap that might be there in the sample processing. You don't want those, you're not interested in those, so why do you want to carry those all the way through the sample processing? It does not make any sense. So again, keep it simple. We want our samples in the very end to be very simplistic things that we can run and that we can analyze. So separatory funnels are great for these types of extractions, and we can easily accomplish them with manual methods. And then finally, microwave assisted is another extraction method that we can use. And these are just like fancy lab microwaves. That's what these are. The problem though is that these are tens of thousands of dollars, depending on how large they are and what kind of bells and whistles that we will have for these. It is not uncommon for these to go $30,000, $40,000, $50,000 here. So if that is the case, that's okay. And maybe you process things with a microwave all day, every day. We just don't. So that's why we've never went that route. The microwave assisted is kind of a substitution in a roundabout way for a water bath or some type of heating exchange that needs to take place. So the microwaves are going to hit it with extreme amounts of energy. It's going to allow you to process samples much faster. And this is great because if I've got a lot of samples that need extensive long periods of heating, then my microwave can take care of that. Maybe more than one sample at one time, absolutely, if that is a thing. If that's what I'm after and that's what I want, great. That's an option for you. And we can process them much faster than more manual types of let's heat it up and cook it on the stovetop or put it in the oven. Microwaves will cook your food much faster. Microwaves will treat and cook, quote, our samples faster in a laboratory environment. So that's where this video is going to stop. In the next video, we're going to continue on and we're going to talk about applying the samples. So now that I have this idea, I've got this sample that's been given to a lab. I need to do something to extract the components that I want out. Now that I have this idea of what's going on, how do we now get those cleaned up sample extractions onto our plate? What are some of the things that I need to watch out for? So that's what we're going to talk about in our next video.